Hi everyone. In this video, we will discuss limits and continuity, continuing our review of material that you would have seen in previous calculus or possibly real analysis courses. So to begin with, one thing that's often sort of overlooked or maybe misstructured in the teaching of Calculus 1 is we tend to sort of jump right into talking about limits without motivating why limits are something that we even care about. So if we sort of skip ahead briefly to the idea of a derivative, we can imagine, like, let's just take the function y is equal to x squared. And let's imagine that we were tasked with finding the slope of the tangent line to this function at some point x is equal to a. So sort of geometrically, right, I could represent that tangent line. Well, that's not a great job, but hopefully you get the idea, right? So the line that sort of just comes up and touches this function, right? I want to find the slope of that tangent line. Well, typically, if I think about a formula for slope, right, I need 2 points. So um, if I want to use sort of my typical slope formula, right, I'd like to have 2 points. So the idea, or one possible idea for how to deal with this, right, would be to select some other point. And we probably want it to be close to A, but it doesn't have to be right at A. So maybe we'll call it A plus H. So H just represents this amount by which we've increased, right? And so now if I look here, okay, this goes up to another point on the function. Okay. Now, respectively, if I come across here, this takes me to the function value. This is f of a, or in our case, right, that's just a squared. This takes us across to some other function value. This would be f of a plus h, right? And now I have 2 points, right? I can define the slope of this, we would call this a secant line. Right? I can define the slope of this secant line between these 2 points. Now that I have the secant line defined, I can calculate its slope. So the slope would just be the difference in the y coordinates divided by the difference in the x coordinates. Again, this is just the standard slope formula here. And now I could simplify that in this particular case. So in this particular case, my function is just y is equal to x squared. So this is just going to be a plus h squared minus a squared all over. Now here I have an a plus h minus an a. This is just all going to be over h. And if you FOIL this out, simplify, you'll end up with a 2a plus h times h divided by h. Now, if you sort of don't think much about what you're doing, you go, okay, I'll cancel these h's. I'll be left with the slope being 2a plus h. And then, well, I really want to think of this h as being really small. I want to think of it as being like 0, right? I want to think about what happens as this point gets closer and closer and closer to a, right? So you just say, okay, well, let's just take that to be 0. And so that will give me a slope of 2a. So that's just taking h to be equal to 0. Okay. And if you remember some calculus, right, the derivative of x squared is 2x. The derivative gives us the slope of the tangent line. So the derivative of this is 2x. So at x is equal to a, that's 2a. It gives me exactly sort of the right answer. Now, it's sort of, again, important to note, sort of historically, right, a lot of the stuff we're going to talk about in analysis we're really proving things that people understood long before they understood the proofs, right? So people were sort of okay with this notion of doing things, but mathematically there's a problem. So mathematically here, so here I'm just defining the slope. Here I'm just plugging in what these functions are using the definition of the function. Here I'm just doing some algebraic simplification. But then to get from here to here, to cancel that h, I have to make the assumption that h is not zero. I can only cancel an h in the numerator and denominator if h is not zero. But then in the next step, right, I make the assumption that h is zero, right? So I have a problem here because I've assumed two contradictory things, right? I have assumed both that h is not zero and h is zero, which is a contradiction. So the question becomes, and really the motivation for discussing limits is to try to deal with this idea. How do we deal with this contradiction? On the one hand, I sort of feel okay about this. Well, I don't want h to be equal to zero because I'm thinking about this secant line. So I want these to be two distinct points. But somehow at the end, I want to talk about what happens as this point gets really, really close to this point. But maybe I don't want to exactly allow it to be the same point. I don't want to allow this point to be zero. So the whole reason we really need the notion of limits turns out to be very useful in a lot of other things. But one of the reasons is because it really helps us make rigorous sense of a definition of a derivative. So what we want to do then is start by trying to make sense of this notion of a limit. And I'll start by sort of giving you a bit of historical context. One early definition of the derivative, sorry, of the limit is due to Cauchy. And this is sort of the translated version here. So when the successive values attributed to a variable approach indefinitely a fixed value, so as to end by differing from it by as little as one wishes, this last is called the limit of all others. Like a lot of older mathematics, you read this, it takes some time to parse through. So if we sort of try to make sense of what that might mean in sort of more modern notation and language, in a lot of ways, what Cauchy was saying was, well, the limit as x approaches a of f of x is equal to L if we can make the values of f of x arbitrarily close to L by taking x sufficiently close to, but not equal to, a. Okay. So conceptually, this is a really good way of thinking about a limit. It allows us to sort of gather some evidence for what we think limits might be. So, for example, if you were curious, to know what is the limit as x approaches, say, 1/2 of 1 over x, okay, now we know that that's just going to be 2, okay, but we might start to justify this, right, by thinking about, and this is often how you might start in a calculus class thinking about limits, right? Okay, well, what if I take x values that are getting, say, closer and closer to 1/2, right? So I could start by looking at, say, 1, and 1 over 1 would be 1. Okay. And then I could say, okay, well, I need something a little closer. How about, 3/4? Okay. And that would give me 4/3, which you'll notice is a little bit bigger than 1. It's closer to 2. And then I could go a little bit further. I could say, okay, well, what about, um, uh, let's go down to eighths. So how about 5/8? That would give me 8/5. So 8/5, that's like 1.4. So, roughly this was 1. This was 1.3 repeating. This is sorry, I said 1.4. It's 1.6. Okay. And we could keep going in this way, right? And we would notice that as we do this, as these values sort of appear to be going to 2, okay, these values appear, sorry, as these values go to 1/2, these values appear to be going to 2. Okay. So again, this is a good conceptual definition, but there are also some problems, right? I mean, if we just start to think, sort of about this a little more rigorously, some of this terminology, things like, what does arbitrarily close mean? In a similar vein, what does sufficiently close mean? Like, what is sufficient? What is arbitrarily close? It somehow doesn't get into the kind of mathematical precision that we want to have to be able to prove statements. So if we want to be able to prove statements about limits, we're going to need to modify this definition to give us something a little bit easier to work with. Now, anytime you're given something mathematical that can be computed, I think there's actually, I mean, there's the natural question of how do I compute this thing? But before you even do that, you sort of like to know, right, that it's going to be sort of well defined. Now, what does well defined mean? Well, that sort of depends on the context. But let's take the case of limits, right? I'd like to know that either a limit exists or it doesn't exist. Okay, right? So that's just sort of like logically one's going to exist or it's not. And if it is going to exist, I might want to know that, well, maybe there's just one of these. Or if there's more than one limit, maybe there are 2 or 3, but I'd like to know sort of when I can stop looking, right? How many are there going to be? So the first result, and we're not going to prove these results today. We'll actually go back in our second pass through and prove a lot of things. But the first thing to recall about limits is just that if a function has a limit at a point x is equal to a, that limit is unique. There's only one limit if it exists. Now, it also may not exist, right? We'll look at some examples in a bit. But if the limit does exist, it's unique. And therefore, we sort of can narrow down, like, I know there's only going to be one limit if I can find one thing that is the limit, that's it. I'm done solving the problem. This is not necessarily earth-shattering. It's not like a result that you sort of look at and go, wow, I didn't expect that. But it's a really nice sort of foundational thing to keep in the back of our mind, right? I just have to find a limit and then I'm done, right? And that makes for really nice mathematics. So now, if we want to prove things, though, we still need a better definition, okay? And so from this, we're going to start with this formal definition of the limit. Now, we will actually modify this definition a bit later on for reasons that I'll explain here in a few minutes. But this is a perfectly good definition of the limit for a function f, which is defined on an open interval I containing a, except possibly at a itself. Okay, so here you see the definition. We say that the limit as x approaches a of f of x is equal to L if and only if for every epsilon greater than 0, there is a delta greater than 0, such that for every x in the interval I, if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. Let's draw a picture to help us understand what's going on in this definition. So the first thing to think about here is we have a point and we need a function that is defined on some open interval I, which contains a. So we have some open interval I. It doesn't need to be a nice, doesn't say it has to be a nice symmetric interval, right? Just needs to be some open interval containing I. But the function may not need to be defined at a itself. It may or may not be. So it says except possibly at a itself. So just to sort of illustrate this point, I'm going to make my function not defined at a. So I have some function here, which, does whatever. Maybe it looks like this. So it's defined on this open interval I, so it's not necessarily defined at the endpoints. It's not defined at A, but it's defined at every point in the open interval I except at A. Okay, so this in pink here, this is my function f. Okay. Now, graphically, if I'm looking at this, right, I want to think about as my x values get close to A, right, what's happening to my function values. So if I sort of imagine, on each side, I have this wall that I'm approaching, I look at what's happening to my function values. Well, from this side, my function values seem to be approaching like this value. Notice the same thing is happening from the other side, right? My function values seem to be approaching this same level here. So that's my limit L. Okay. So again, we've used that conceptual definition to help us think about where L ought to be. Now, how does this formal definition work? So the formal definition, basically, I think of it as a challenge, right? So you claim that the limit as x approaches a of this function is L. And I say, okay, great. If the limit's actually L, then I'm going to challenge you to get all of your function values within, say, 1/10 of L. Okay. So that's like taking my epsilon to be 1/10. Okay. So I come here, actually use a different color here. So I come here, and this gives me a little epsilon band around L. So I go up and down by epsilon, and that gives me a little epsilon band. So all of the points that are in this vertical band here are within epsilon of L. All the y values of these points are within epsilon of L. So then you say, okay, well, look, if my x values, you say, I'm going to pick a delta. Now, your delta, you're going to pick to be this big. Okay, because notice that if you take any x values within delta of A, right, so this is going from A minus delta up to A plus delta. If you pick any x values in this delta band around A, then their y values will be between L minus epsilon and L plus epsilon. Okay. And you want to be able to do this for every epsilon. So the first time I challenge you and say, can you pick a delta band around A so that your function values are always within 1/10 of L? And maybe you do that. And I go, okay, well, that was too easy. Can you do it for epsilon is 1/100th? And so then you go back and recalculate and you get another delta, right? And you say, okay, I can do it for 1/100. And then I keep challenging you. And so eventually what you do is when you do these sorts of epsilon delta proofs, is you provide a winning formula. You basically say, hey, look, I'm tired of you asking me about specific epsilon values. If you give me any epsilon, here's how I will calculate my delta so that if the absolute value of x minus a is between 0 and delta, then the difference between my function values and L in absolute values will be less than epsilon. Now, we're not going to practice a bunch of delta epsilon proofs right now. We will actually do them once we sort of start our second pass through. But this is sort of conceptually the idea of the delta epsilon definition of a limit. Now, a couple of notes about this. The first thing I want to note is that if we just go back and look at the formal definition does include several of the features that we had in our informal definition. So if I look, for example, here, if I come right here, so this half of this inequality, notice that this definition is saying I don't care what happens when x is equal to a. So I'm not worried about what the function is doing at x is equal to a, because if x was equal to a, then this difference would be 0. And I'm specifically excluding the equals 0 case. Okay. On the other hand, right, the sort of second half of this inequality is saying I'm worried about what's happening when x is close to a, when that distance is smaller than some delta, right? And what I'm doing is I'm looking at these cases both. I want to make sure x is not equal to a, and I want to make sure x is close to a. And then what I'm trying to do is show that the function values are close to the limit values in those cases. Okay. So the key is you show that you can get the difference between your function values and your limiting value arbitrarily close within an epsilon by making sure your x values are within a delta of a. Okay, that's exactly how we formalize this definition. Now, I mentioned that we'll later modify this definition, and the reason we will do that is you may want to eventually think about some other sort of, you might think of them as sort of counter or some like weird examples or some edge cases, but like what about this function? So what if I take the function which is just 1 at a? So literally the definition of this function would just be f of x is equal to 1, and the domain here, I'm defining f to be from the singleton a into R. Now, in some ways, you want to look at this and go, that's just a weird function. Like, I don't sort of stop asking me weird questions, right? I don't know. This is a weird contrived function. But in math, we want to be able to write definitions that work for every case. Now, you could sort of have, two options. You could say, well, the limit just doesn't exist here. It doesn't exist today. There's no way to talk about it. And using this definition, right, this function is not defined on an open interval I containing a except it's only defined at a itself. So this is not a function for which this definition would apply. However, maybe we want to be able to talk about a limit, but it's sort of hard to say because I don't know. It's just a weird singleton point. So we'll need to deal with that. Now, you may say, okay, well that's fine. That's a case we can deal with. But what about then the following example? What if I expand the domain of this function and I say this is going to be a function from the set A. Well, let's actually, sorry, A plus 1 over n, where n is a natural number, okay, into R. Now, it's still, all the function values are still 1, okay? But now this function, so it's actually, this function now is not defined at A. A is not in the domain, but it is defined at a bunch of points over here. So, for example, it's defined when n is 1. This is A plus 1 over 1, and that has value 1. It's defined, so that's A plus 1. It's defined at A plus 1/2. It's defined at A plus 1/3, and A plus 1/4, and A plus 1/5. So you start to get the notion that there's sort of all these dots. They're all distinct, but they're all sort of leading up to here. And now you ask the question, well, can you talk about the limit as x approaches a of this function? Now, this is in some ways even weirder than the last one because this function isn't even defined at a, but now I start to feel like, well, maybe I should be able to talk about the limit as x approaches a here. I have like in some appropriate sense of approach, it feels like I have points that are approaching a and the function values are all 1. I feel like I should be able to say that the limit approaches a, the limit as x approaches a of this function is 1. But again, this definition doesn't apply because my function isn't defined at an open interval containing a. So there are these weird other edge sorts of cases that I need to deal with. And that's going to require thinking a little more carefully, both about the structures of domains that we allow, and then how we want to define the limit sort of in some of these edge cases. So again, we're not going to solve that problem today. That's just sort of a reminder that there are some weird cases that this epsilon delta definition we've already put up doesn't deal with, that we may want to, generalize our definition a bit to be able to handle. Now, just briefly, I'll mention another nice thing about that definition we just had is that it can very quickly be modified to deal with one-sided limits. So if you recall, instead of thinking about the limit as x approaches a from both directions, you could restrict yourself to only coming from one direction, and you could talk about a one-sided limit. That just briefly changes some things. So if the limit as x approaches a from the left of f of x is equal to m, and the limit as x approaches a from the right of f of x is equal to n, sorry, we say those are true if for every epsilon greater than 0, there is a delta such that, okay, if we're talking about the left-handed limit, then we want to say if 0 is less than a minus x is less than delta, then f of x minus m in absolute values is less than epsilon. And then something analogous for the right, but we've just put x minus a instead of a minus x there. Now, notice that these look almost identical to the original limit definition. The original limit definition had this. Okay. Now, this necessarily meant we were looking at x values that were not equal to a, but if we were to break this up in sort of terms of absolute values, like we're really looking at both of these cases. We're looking at 0. If x was bigger than a, we were looking at this. So this implied that we were looking at this case or sorry, as well as this case. Sorry, my marker here is drying out a bit. Less than. Okay. So notice this is exactly what we have defined here, right, as the right-handed limit. And this, if I just do a little, if I negate everything here, which is also going to flip all my inequalities, this is equivalent to, this one becomes equivalent to 0 is less than a minus x is less than delta, which is our left-hand limit definition. So all we're doing is really changing this condition that appeared in the full definition of the limit, and we're breaking it up into these left and right-hand cases. Okay, so you can also define that. And then it turns out, because as we can see here, if we're looking at these x values, then we're looking actually at both of these. And actually, if the statement holds for both of these, then you can combine to get back here. This actually gives us very quickly a nice little theorem, which actually I haven't put in the slides, but you might remember from calculus that the limit exists and is equal to L. If the limit from the left exists, the limit from the right exists, and they are both equal to L. So it sort of falls out this nice result about one-sided limits. All right. Now, quickly, I'll just remind you, and these again all follow, and we'll prove some of them. They all follow from that definition of a limit. But if you have two functions f and g, and both of them have finite limits as x approaches a, so that is to say, like the limit as x approaches a of f of x exists, the limit as x approaches a of g of x exists. And if you have some real number, then you can do all this sort of nice algebra. So this first one, right, just says I can pull a constant out of a limit. So if I have the limit as x approaches a of c times f, that's the same as c times the limit as x approaches a of f of x. I can break limits up over sums or differences. So if I have the limit as x approaches a of some function plus or minus another function, then I can just rewrite that as the limit of the first part plus or minus the limit of the second part. Okay. Now remember, this assumes that you already know that these two things exist, these two individual limits exist, then you can calculate the limit of the sum. You can do the same thing with products. So limit of the product is the product of the two individual limits. And you can do the same thing with quotients, except you have to be a tiny bit careful about what happens if the denominator is 0. So the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, as long as this limit in the denominator turns out not to be zero, right? And of course, you need that because if this limit turned out to be zero, then this expression would be undefined. Okay? So these are really helpful things when we're actually calculating things with limits. Now, all of this leads us to the notion of continuity. Okay, so one of the first sort of well, anytime you have a class of mathematical objects, in this case, we're going to be thinking a lot about functions. So when you have a sort of bucket full of functions, the first thing you start trying to do is you start trying to understand what are nice like groups of functions that live inside of here. And so you may, already have some notion of some nice types of functions, sine functions, right? Or sorry, yeah, like the sine function is a nice function, the function x squared. So you sort of start with just individual functions, but then you might build up classes of functions. So trig functions, polynomial functions, quadratic functions, and right, some of these are subclasses of each other, right? But you want to sort of it becomes an interesting question where you want to define some class of functions which is large enough to be interesting, right? Large enough to have several things in it, right? To be sort of interesting, but it also needs to be interesting, right? Which is to say that I want to be able to say something about this class as a whole. So to sort of give you an example of how this could go wrong both ways, um, you can write down a definition. You can define anything you want, right? It just turns out that not all definitions are useful. So I could define, say, a Quinn-like function to be any function which is continuous and whose integral, and so that the integral of the absolute value of that function is equal to zero. That's a perfectly fine definition. Okay, a Quinn-like function is any function which is continuous and such that the absolute value of its, such that the integral of its absolute value is zero. The problem is there's only one such function, and that's the constant function zero. That's not a very interesting class of functions then, right? In fact, it's only one function, and I could just call it by its name, right? So on the one hand, I have to be careful when I define something that I don't define it so narrowly that there's like nothing in there to be interesting. I could define it so narrowly that there's actually nothing that satisfies those criteria. Okay. On the other hand, right, if I just take the set of all functions, so many weird things can happen within the set of all functions that I can't really say much else about it, right? So we're going to define a continuous function, and then what we're going to see is that there are actually a nice number of continuous functions, and we'll just name off a couple, but also that we can say some interesting and cool things about continuous functions. All right, so let's first define continuity. So the function f, we say the function f is continuous at x is equal to a, if and only if the limit as x approaches a of f of x is equal to f of a. Said another way, a function is continuous at a point if the limit of the function at that point and the function's value at that point are the same. Now, anytime you see an equality like this, it may be helpful to think about any equality as sort of three things. If you have left-hand side is equal to right-hand side, that's really making three claims. It's saying the left-hand side exists, it's saying the right-hand side exists, and it's saying that those two values are in fact equal to each other. So if we think about this in this context, right, we can really think about this as saying three things. So the first is that it's saying the limit exists. The second thing it's saying is f of a exists. You could even rephrase that to say a is in the domain of f. Right? That means the function f is defined at a. And then finally, if both of those things are true, great, then I need to check that they're in fact equal to each other, right? So this definition really is sort of telling me three things. It's telling me that I need the limit to exist, I need the function to be defined at that point, and I need the value of the limit to be the same as the value of the function at that point. Okay? If I have all of those things, then my function is continuous at that particular point. Now, we often speak not about functions that are not about functions that are continuous at a point, but we just talk about continuous functions or functions that are continuous on their domain or functions that are continuous on some interval. A function is continuous on an interval if it is continuous at each point in that interval. So here we're defining continuity at a single point, but if we want to talk about a function that's being continuous on the interval 0, 1, all we're saying is that function is continuous at every point between 0 and 1. Now, you already know lots and lots of nice continuous functions. In fact, probably most of the functions you can think of off the top of your head are either continuous everywhere or they're continuous on their entire domain. So to give two quick examples, all polynomial functions are continuous everywhere. So negative pi times x to the 57th plus 3x cubed plus 19, that's a polynomial. It's continuous everywhere for any value of x, right? That function is continuous at every point. Rational function. So you'll recall that a rational function is just polynomial function divided by another polynomial function. Rational functions are continuous wherever they're defined. So another way of saying that is they're continuous on their domain. So anytime you can define, like anytime you can plug a value into the rational function and get some value out, then the function is continuous there. You can actually say a little bit more about rational functions, which is that they have sort of nice discontinuities. So the places where they are discontinuous, those discontinuities are either removable. A removable discontinuity maybe would be something like this. So a removable discontinuity is just one where, if I could go in and define the function value, I could just sort of fill in that hole there. More formally, the discontinuity is removable if the limit exists, but the function value just doesn't exist. Okay, so this, I need to take that point out now. Right, so there's a removable discontinuity. An infinite discontinuity just means one of the, at least one of the, at least one or possibly both of the one-sided limits are infinite or minus infinity. You might say, well, wait, what other ways are there for a function to be discontinuous, right? Of course, you can have a jump discontinuity. Okay. So that would just look something like, right, maybe I have this and then this. So in that case, the limit doesn't exist at all, right? Because you have different left and right-sided limits. And then there's another type of discontinuity, sometimes called an essential discontinuity. This one is a little harder to draw, but I think I can give you the idea. And if you want an example of such a function, sine of 1 over x as x goes to 0 has an essential discontinuity. Okay. And what happens is it's oscillating, and as you get towards 0, it starts oscillating like infinitely fast. And so you get this sort of, behavior that looks something like this. So at 0, this is not defined at 0, right? So I guess I should, make sure I don't have anything defined at 0, but it's defined everywhere else. But this is just a really bad discontinuity. Here, the one-sided limits don't exist. It's not defined at the point, like lots of bad things going on here. But polynomial functions, continuous everywhere. Rational functions, continuous on their domain. trig functions continuous on their domain. Exponential functions continuous everywhere. Like lots of the functions you know and remember, that you've worked with since maybe say a pre-calculus course, most of them are continuous on their domain. But continuity includes just sort of this broader class of functions that you may not even be able to write down expressions for, but they all happen to have this same nice property, right? The limit is equal to the function value. All right. Now, some things follow from the definition of continuity. And you'll notice that these look a lot like the algebra of limit properties, and that's because really they're exactly the same. So this just says if f and g are both continuous functions at a point x is equal to a, then any constant times f is also a continuous function. The sum or difference of two continuous functions is continuous. The product of two continuous functions is continuous. And if I take the quotient of two continuous functions, then they will be continuous at x is equal to a, so long as g of a is not 0, right? This is really nice. It follows immediately from the properties. So, sorry, from the definition. So if I know f and g are both continuous at x is equal to a, well, what does that tell me? So if I then look at the limit, so let's say we wanted to sort of prove the second one here in the plus case, right? So I would want to look at this. So I want to look at the limit as x approaches a of the function f plus g of x. Okay. Well, what is that? That's really going to be the limit as x approaches a of f plus g of x is just the function that's defined to be f of x plus g of x. Okay. But now, because I'm assuming that f and g are both continuous, that tells me that the limit as x approaches a of f of x exists, and the limit as x approaches a of g of x exists. And therefore, since each of these individual limits exist, I can use the algebra of limits properties to rewrite this as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Well, now I also know what this limit is because f is continuous. Since f is continuous at a, the limit as x approaches a of f of x is just f of a. Similarly, because the limit as x approaches a of g of x, this has to be g of a because g is continuous at a. And now f of a plus g of a, that's just f plus g, the function f plus g evaluated at a. And so, right, what I've managed to do is show that this is equal to this, which shows that f plus g is continuous at x is equal to a. You can repeat almost word for word this argument to prove any of these other properties, right? So my point is that all of these algebra of continuity properties, they just follow directly from the algebra of limits properties. Now, this also starts to give me actually a bunch more continuous functions because now, let's say I know that trig functions are continuous on their domains, polynomials are continuous everywhere. So now I can take a polynomial, say x cubed, and I can take a trig function, say sine. Both x cubed and sine are continuous everywhere. And now I know the function x cubed plus sine of x, which is neither a polynomial nor a trig function. The sum is neither of those. But now I know that the sum of those two has to be continuous. So I can take two continuous functions that might sort of be from different classes of continuous functions. I can add them together to create a new function, or I can multiply them, or I can divide them, right? So these are all really nice, these are nice properties to have. All right. So now the question becomes, we've now sort of established there are some interesting continuous functions. But now the question is, well, but what's interesting about continuous functions, right? What can I say about this class of functions? Now, you might remember from calculus, you probably talked about three important theorems, which are sometimes called the value theorems. So there's the intermediate value theorem, the extreme value theorem, and the mean value theorem. Now, the mean value theorem has to do with derivatives, and we'll talk about that more in a later video. But quickly, we want to talk about remind you about the intermediate value theorem and the extreme value theorem because they are both theorems about continuous functions. So the intermediate value theorem says let f be continuous on the closed interval ab. If c is any value between f of a and f of b, then there is at least one x value in the closed interval ab for which f of x is equal to c. Let's take a look at how this works by thinking about a picture. Okay. So I'm going to assume that I have some function which is going to be defined on a closed interval AB. So let's say my function looks like this. Okay. So if I sort of write out over here, here's f of A. Here's f of B. Okay. And what the intermediate value theorem says is, well, pick any value you would like between f of A and f of B. That's going to be our C. So let's say I pick a C value that's right here. Okay. Now notice that if I go over here, okay, here is a spot, this is going to be my X, where f of X has to be equal to C. Okay. The intermediate value theorem says for any value you pick between f of A and f of B, there's going to be some point where your function hits that value. Okay. If I were to choose a different C value, so I could go up here, choose a different C value. Now you would actually see here, right, I get sort of potentially three different X values that could work. The intermediate value theorem guarantees me that there is at least one, but it doesn't say there can't be more. And there can be one or three or 7 or 12 or I mean, it depends on the function. It depends on the particular C value. But it does guarantee me that there will be at least one. Now, one way to think about the intermediate value theorem is it really tells you that your continuous functions can't have any jumps, right? They can't jump over certain values in the domain, or sorry, in the range. So they have to actually hit every point between f of A and f of B if your continuous function starts at f of A and ends at f of B. Now, the intermediate value theorem is often sort of employed to show things like, oh, a function has, a zero in some particular interval. So, for example, if you have a function and you know, say, your function, so let's say you know that you have some function and all you know about it is that one, it's continuous. Let's say it's continuous everywhere just to make life easy. Let's say you know that at -1, your function has the value -3. Let's say you know that at 7, it has the value 1. Okay. If you know this function is continuous, then you know that somewhere in between it has to hit 0. Why? Because 0 is a value between -3 and 1, between f of A and f of B. Your function is continuous on the closed interval AB. And so by the intermediate value theorem, any way you're going to connect these 2 points, right, you have to cross 0 if your function is continuous, right? You can't jump over it. So maybe it's there. But again, I don't actually know what this function looks like. All I know is that it's continuous, that at -1, its value is -3, and at 7, it's 1. I don't know where this value is. I don't know how many times it might cross 0. But I know that it crosses the y value of 0 at least once. That's what the intermediate value theorem tells me. So it's often invoked to sort of prove that Certain types of equations have solutions. Certain types of functions have roots, things like this. Now, the other value theorem that deals with continuity is the extreme value theorem, which says again, it starts let f be continuous on the closed interval AB, then f is bounded on AB, and f achieves a maximum and a minimum. Said another way, it means there have to be two x values. We'll sort of call them x. So the book writes at x sub little m and x sub capital M. I'm going to call this x min and x max. So there exists two x values, x min and x max, in your interval AB, such that at x min, your function actually achieves the minimum value on the interval. And at x max, your function actually achieves the maximum value on the interval. Now, you might wonder sort of, I think it's easy to look at this and go, well, wait, how could it be that that doesn't happen? Well, imagine if you don't, now again, I'm going to have to break one of these properties. So let me start by showing you sort of what this is really saying. So if I have some interval AB, I have a continuous function on this interval, I can do whatever. Okay, here's my function. Now it's easy to look at this and sort of identify, okay, here's my minimum value. So I'm going to call, so this would be like my minimum value. It's not working. This is going to be my minimum value. This is the minimum over AB of f of x. And maybe my maximum value looks like it's probably here. Okay. But what this says is my function actually has to achieve those values. So here, this would be x sub capital M, and this would be x sub lowercase m. Now, again, we're looking at a continuous function. This has to happen. So you could very reasonably ask the question, sort of, wait, how could this not happen? Well, let's look at a discontinuous function. And now you can imagine maybe even something as simple as this. So I'm going to make this almost like a little parabola. But what I'm going to do is right here at the peak, I'm going to introduce a discontinuity. And now what has happened is, notice that the maximum value, right, still needs to be sort of up here. I'm just going to abbreviate this by just writing max for now, right? The problem is at the point where you want it to be, the function value, you have this sort of jump discontinuity here, this like removable discontinuity here, and now you have a problem because your function never actually achieves this value. So it's sort of a problem because you can't go, oh yeah, okay, my maximum value is achieved at this point. You sort of have this issue that it's approaching your function values are approaching the maximum, but they never quite achieve it. So the extreme value theorem says if I have a continuous function, that can't happen. I have to achieve my maximum value. Okay. Now, I will also say, and some of the problems on the first exercise set will deal with this. It's always important to go through theorems like this and think about, like, is it necessary that it be continuous on the closed interval, right? What if I tried to just say, well, what about an open interval? What could happen then? Would this theorem still hold? The answer is no. What if I tried to change various other things in here? Could I get rid of continuity altogether? We've already seen the answer to that is no. So the question to ask yourself sort of, are these conditions all essential? And what would it look like? What's sort of a counterexample that shows me that I can't get rid of one of these conditions, right? So I'll ask you to actually do a little bit of that and think about some of that on the first exercise set. Now, the last thing I just want to briefly mention about continuity is that continuity is nice because in a lot of ways it just tells you how to deal with limits. So if you have a function that's continuous at x is equal to a, And let's say you know this limit. Let's say you know that the limit as x approaches c of phi of x is equal to a, with the range of phi contained in the domain of f. Then if you want to calculate the limit of the composition of these two functions, you can actually just push the limit inside the first function. And notice that first function is the continuous one. So what this really is saying is if you want to calculate the limit of a composition of two functions, and you know that one of the functions is continuous, you can just push the limit inside the continuous function. Okay, so notice there are some important things here. I need the function to be continuous at a, and the limit of the inside part is itself a. So you got to be calculating the limit sort of at the right point so that the input of the function here is where you are continuous, right? But again, if I look at this, this is really just restating the definition of continuity. In a lot of ways, I'm saying this is the limit as, okay, yes, x is approaching c, but phi is approaching a. So this is like the limit as phi approaches a of f of phi is equal to f of a, right? So this is really just the definition of continuity restated in a way that involves a composition of some functions. And then one other quick sort of, it's really a consequence of the previous theorem, is that compositions of continuous functions are also continuous functions, right? So I mentioned earlier this example of if you have x squared, let's say in sine of x, right? You can add them, you can multiply, but you can also compose them and you'll still get a continuous function, right? So, right, I know that x squared is continuous. I know that sine of x is continuous. And now this would tell me that I could take the compositions of these functions. So taking the composition, if I do sine of x squared, that's one composition. If I do, and that has to be continuous. I can also do it the other way, which is to take sine of x and plug it in for x. So it also tell me that sine of x squared, or sine squared of x, is also continuous, right? So again, this is just another theorem that sort of gives you yet another way of building continuous functions out of other continuous functions. All right. This is going to conclude our discussion of continuous functions. And in the next video, we will jump into recalling some facts about derivatives that you would have learned in a Calculus 1 course.